Yeah, yeah.
How much time do we have for this one class period?
Just one class period for the
class
exam.
Period?
Yep.
And how long should the exam be?
What do you mean how? That sounds like it's going to be an hour and 20 minutes.
No, like, I mean, like, how many questions?
Oh, typically there's 4 questions on it. Yeah. Yeah. All right. So we're going to talk about moments in 3D. And contrary to popular opinion, this actually wouldn't have helped you on your homework, right? So the homework problem was kind of a scalar version of 3D, and what we're going to do is the vector version in 3D. And in order to do that, we need to be able to do the cross product, okay? And the cross product is, oh man, it's a tool. Yeah, Nick says it's a determinant, which that just kind of gives me the heebie-jeebies. So I'm not going to say that. Okay? Good for you. Right? So if we have 2 vectors, we can take the cross product of these 2 vectors. And if they lie in the xy plane, what will it result in? Yeah, a perpendicular vector going straight up. Okay? So the cross product is a way of multiplying 2 vectors. So if this is vector A, and this is vector B, and this is vector C, then C, we would say, we could define as A cross B, which I believe is actually equal to AB sine theta, where theta is the angle between them. Did I do that right? I never do it that way. I want to make sure. Yep, I did it right. Okay? Now, unlike the dot product, and these are the magnitudes, right? So absolute values of A and B there. Unlike the dot product, this is not super easy to compute. Okay? So how you take, I'm going to go ahead and give you some different things. A couple unique things you need to know about cross products is they always result. Wow. We're just going to start that over. Always result in perpendicular vector. Right? So they follow the right-hand rule. So if I did A cross B, I stick my fingers, I point them in the direction of A, and then I curl towards B, and I end up with my thumb sticking straight up. That also says if I took B and I crossed it with A, I take the fingers of my right hand like this, and then I curl them in the direction of A, and my thumb is sticking into the page. Okay? So it does matter, I forget which mathematical property, it does matter to the order. A cross B is different than B cross A. In fact, they're equal and opposite. Right? Okay? So let's say we have 2 vectors. I'm going to define vector A as being 2I plus 3j minus 4k. And I'm going to define vector B as being 5I plus 6j plus, what do you think in the k? 7k. Good work. Okay? And this is, they're all plus each other. Okay? Now there's lots of different ways you can learn to do a cross product, including putting it into your calculator. There's a cross product function. You can do little x's and determinants and things like that. I find the easiest way to do this is to put I, j, and k like this. Okay? And then I go along the diagonals. So I'm going to go like this. Okay, so I'm going to say that C, which is the cross product of A cross B, would be equal to 3 times 7 is 21 I hat plus j diagonal. And to do this well, you really need to write the vector twice. So you'd say 2, 3, 4 again, and 5, 6, 7. Okay? I know this is messing with you guys because this isn't how you learn to do cross products, but it's how I learned it, and I like it better than your way. Why does that mean? I'm not saying that it is better, I'm just saying that I like it better. Okay? So the first value was 3 times 7 is 21i. The next one's going to be 4 times 5j, that's 20j. And then the last one is going to be, hold on, yep.
You're doing great.
2 times 6k plus 12k. All right? Everybody good? You can do that so far? So when you're going down and to the right, you're positive. When you go down and to the left, you're negative. So now I'm going to go 4 times 6 is 24i, so minus 24i minus 14j minus 15k. Okay, and I put that all together, so I'm going to have my cross product of A cross B is going to be 21i minus 24i. That gives me negative 3i. 20j minus 14j, that gives me plus 6j. And 12k minus 15k, which is negative 3k. All right? That is the mathematical operation for taking a cross product. That's the one I'm going to use, and that's the one I'm going to cover. If you haven't taken 254, I highly recommend using what I just showed you. Okay? It works 98% of the time, 100% of the time. Okay? Questions on the cross product? It really is just diagonals and then backwards diagonals. So here, I'm going to give you two more vectors. D, I'll give you as negative 3i plus 3j plus 3, no, I should use different numbers. I'll do 3i, 2j, 1k, ooh. And E, I would like you to do 7i minus 5j plus 4k. All right? And I want you to find F, which we'll say is D crossed E. Okay? Please do it by hand, not in your calculator. Okay. So D cross E, I'm going to put D on top. 3, 2, 1, 3, 2, 1, 7, negative 5, 4. Oops, and that was negative 3, 2, 1. 7, negative 5, 4. I, J, K, I, J, K. So go diagonal. First, we'll have, oh, they didn't do this very well, but there we go. We'll have 8i, looks like plus 7j plus 15k. Then we'll have minus 5 plus 5i, right? Because it'd be negative I times negative 5, which would give me plus 5i. Plus 12j, right? Negative j times negative 3 would be 3j times 4 is 12. And then negative 14k. And if we put those together, then f would be 8i plus 5i is 13i. 7j plus 12j is 19j. And 15k minus 14k is 1k. Everybody get that? Okay, that's a cross product. Neat thing about the cross product is if we come back here, the magnitude of A times the magnitude of B times sine theta. All right? This is why we use this in moments. Okay? Let's imagine for a second we have a coordinate system. Well, yeah, I could move the paper, sure. It looks like this, okay, where x, y, and z. And let's say we're interested, this is our point that we're interested in, point O. And we know that there's some force vector going in this direction, right? Lies in the xy plane. Okay. But I know that maybe it crosses the y-axis right here. Okay. So I'm going to call this my position vector, right? So there's the force vector and there's the position vector. Now, recall that a moment is equal to a force times the distance. And what's important about that distance? Yeah, Rebecca's got it. It's the perpendicular distance from the point of interest. So if I said O here, from O to the line of action of the force. So that's really actually going to be someplace back here, right? This is the D we're interested in. Agreed? Okay. Now, if I call this theta, would you agree with me that D would be R sine theta?
Sure. Yes.
Yeah? Thank you, Brendan. You're an agreeable guy. Okay? Does everyone see that D is going to be R sine theta? So then if I multiplied that times the force, right, this would give me the scalar magnitude of the moment about O. Right? But what's slick is that by using the cross product, R was not perpendicular, was it? Okay? So if FR sine theta, if we go back up to our definition, FR sine theta is equal to, FR sine theta is going to be equal to R cross F, right? So we can take the cross product of any vector R from the point of interest O to the line of action of F and take the cross product of that with the force, and we'll get the moment about O caused by that force. This is super handy, all right? Because what this allows us to do is we don't have to find perpendicular distances, right? In scalar analysis, we didn't do that either. We broke it into xy components, and then it was pretty easy to find perpendicular distances. But in 3 dimensions, that's really hard. So what we do is we use the cross product, all right? So now you can bust out your packet, and let's look at problem 428 here. Okay. So we're asked to determine the moment of the force F about point P. Express the result as a Cartesian vector. Okay. So we know that the moment vector is always going to be r cross f. It's not f cross r. It's always r cross f. You take the position vector r towards the line of action, then you curl your fingers in the direction of f, and you get the sense of the vector. Okay, it's going to be perpendicular to that plane. Can you visualize that here? It's like a kind of stick your fingers from P to A and twist them. I can't see that very well, but let's put it on here. Oops. Okay. So RPA, we need to figure out what the position vector of P to A is. We do that by what? The displacement vector, right? So it looks like in the x direction, I'm going out 1. So let's say it's 1 I hat. In the y direction, it looks like I'm going from positive 4 to negative 2. So it looks like I'm going minus 6 j hat. And in the k direction, I'm going from 3 to 6, so plus 3 k hat. All right? So then my moment vector is going to be the cross product of RPA crossed with F, or 1 minus 6, 3, 1 minus 6, 3, negative 6, 4, 8, negative 6, 4, 8. Right? Then we'll throw on our IJKs, I, J, K, I, J, K. So the moment vector is going to be negative 48 I hat, negative 18 j hat, 4 k hat, minus 12 I hat, minus 8 j hat, minus 36 k hat. So I believe the moment vector will be negative 60 I hat, negative 26 j hat, negative 32 k hat. Anybody else? Looks good? Okay. So where is this? If we tried to draw this, negative 60i is very negative in the x, negative 26j, pretty negative in the j, and negative 32k, pretty negative in the k. I'm going to say that this is like someplace back in there, I guess, right? Again, stick my fingers in the direction of the position vector, curl in the direction of f, and I'm going to get this vector that's kind of doing that. Yeah, Max? Negative 12i. Because it's I times 3 times 4, and then when you're going back and to the left, you always put a negative in front of it. Yeah, Sean. So this is the moment vector, right? This green guy I've drawn here, and actually it should be applied at P, right? So this is the axis about which P is trying to be twisted by F. Okay, so this is, imagine if I'm at P and I pin it in 3D space and then I push with this force vector F, right? The axis about which I would be rotating my paper now would be along this direction. Okay? And if we wanted to know its magnitude, right, we'd have to say 60 squared plus 26 squared plus 32 squared, square root that, and that would give me the kilonewton meters magnitude of the moment. Excuse me. What'd you get there, Travis?
72.8.
Wouldn't the axis about which you're rotating be P?
P's not an axis, it's a point.
That's where you're rotating around though, right?
Yes, but that's just the point, and I'm telling you, I can tell you the direction you're rotating, like what direction the axis is that you're actually purely rotating about. Because P, you could rotate about it, if you just say I'm rotating about P, that doesn't really, in 3D space, fully define what's happening. Okay? All right, so there's a moment of 72.8 kilonewton meters about P by force F being this distance away. Okay, if I want to know the direction of that, I'd need to find a unit vector of this guy, right, of that moment. That'd tell me the just pure direction of it. All right? Lots of dissatisfaction out there. Yeah? What's this for?
Yeah.
This is finding the magnitude of a vector. This is Pythagorean's theorem.
Oh,
Okay, so I'm just finding the magnitude of that vector. You good? Let's try another one then. Okay. Determine the moment of the force F, 80 pounds there, about the door hinge at B. That's right here. Okay. Express the result as a Cartesian vector. This is going to be fun. Sierra's like, I'm not so sure that you and I have the same definition of fun. Okay? I'm going to lay out what needs to happen, and then I'm going to leave you to do it. Okay? So we have a force of 80 pounds. When I say that the moment about B is equal to R cross F, can I just use 80 pounds? No. How would I find the vector F? Close. So I know the magnitude of the force is 80 pounds. How would I give it direction? The unit vector, right? So I need to figure out what RCD is, then determine, so find RCD, then use that to find UCD, right, the unit vector, then multiply by 80. That gives you the force vector. Okay. For the position vector, well, that one you can figure out. You need to figure out a position vector from B to the line of action of F. Now, here's where the tricky stuff comes in. How would you find a position vector from B to the line of action of C? There's an easy way and there's a hard way. I'll give you a hint. If I'm looking for a vector from B to the line of action of CD, do I have to do RBC? Probably not, right? So here's one option. We have enough information to find RBC, right? Does it look fun? Not really. Okay. How about RBD? That's to the line of action of the force, right? Okay. So RBD, I'll just do that for you. looks like it's negative 3.5 I hat plus 3 j hat. Okay. So go ahead and solve the problem. Finish the problem. Find the force vector, and then take the cross product of r cross f. That's a lot of math. Did you guys get something about like that? So I found the position vector. Did you guys all find a position vector like this? Negative 5, negative 5.83, negative 2.83. Does that look good? Okay. Then I found a unit vector. I just used my TI-89 for this. Right? Negative 0.611, negative 0.712, negative 0.346. Everybody else get that? Okay. Then I multiplied that by 80, and I got my force vector. Okay. Once I have the force vector, then I just need to do the cross product of my position vector and my force vector, which I did here. I did this by hand. I realized that's probably not how you're going to do it most of the time. Right? Most of the time, I'd recommend you get this calculator out, you hit catalog, and then you hit the letter C and scroll down a little bit, and it will say, should say cross product here. There it is, cross P. See that guy? You hit enter, open a square bracket, And the first vector is our position vector. So negative 3.5, comma 3, comma 0. Close the square bracket, another comma, open a square bracket, and now do your force vector. Negative 48.9, comma, negative 57, comma, negative 27.7, I think. And then I close that bracket and close the parentheses and hit enter, and I get something that looks pretty stinking close to what I've got there. There you go. That's 83.1, 96.95, 346.2. So got the same thing doing it by hand or using the calculator to do it. All right? So the biggest thing to remember in three-dimensional moments is you're just taking a position vector from any place, from the point you're interested to any place along the line of action of that force. Any vector works. Okay? And then just cross product that position vector with the force vector, and you're in like Flynn. Okay? Now, sometimes we're not interested in just a random moment. Like in this case, what axis does the door actually rotate about? Kind of about an axis parallel to the x-axis that goes through A and B, right? Kind of those hinges, that's where it actually can rotate. So a lot of times we really want to know what's the moment about that axis. Okay? And to find that, we take what's called the triple scalar. Excuse me, the triple scalar product. All right? And that's where what we want to do is we now have this moment, right, in our force. We figured out this moment, and it lives negative I, negative j, positive k. So it's going to live, it's some twisty, right, about B, and it's kind of off in this direction. But I want the projection of that onto this axis. So I want to know how much of that lives right on that axis. Anybody remember how you project a vector onto another one? The dot product, right? And so if I want to know the component of this that lies along that axis, I would take the dot product of the unit vector of that axis. Anybody know what the unit vector of the axis B to A is? Yeah, you do.
Oh.
Look at it.
1j. No, 1i.
Negative 1i. There we go. Brendan got there, right? Because the position vector of RBA is going to be 0, or excuse me, is going to be negative 1, 0, 0. And so the unit vector is just negative 1i. So if I then took the dot product of this, right? So let's dot, thank you, dot unit vector of BA, we'll dot with the moment of B. And this is called the triple scalar because the moment of B, this is equivalent to saying the unit vector of BA dotted with R cross F. That's why they call it the triple scalar product. Okay, because there's three things there. But if we do this, the unit vector of UBA we just said is negative 1 I plus 0 j plus 0 k. And we're going to dot that with negative 83.1 k, negative 97 j, plus 342.6 k. All right? I'm off page 2. So when I take the dot product, I just multiply and add, right? So 0 times 97, it's 0. 0 times 342, 0. So we just end up with the component that's along that axis is 83.1 Newton meters, or whatever, pound feet. Okay. This one was easy because we had it in I, J, and K components. So we could say, well, what's the twist about the that axis? Well, it's just whatever that moment is in the I direction. But there's other times where we're not on any particular axis and we've got to do a dot product. So let's try one of those with the last 10 minutes we have here. Okay. Determine the moment of this force F about an axis extending between A and C. Okay, express the result as a Cartesian vector. So what do we got to do? Find the axis between A and C. What else? How are we going to find the moment of that force? R. Okay, so you guys are tired. The moment, right, is always going to be R cross F, right? What R is this? Excuse me, Jake? Yeah, it's the position vector from the point we're interested in to where the force acts, right? So we're interested in what the effect is along this axis, right? Here's the axis AC. So we just need to find a position vector from anywhere to point B where the force is applied. So we could do that from A to B, or we could do that from C to B. I like C to B. Why do you think I like C to B?
Shorter, less work.
It's got a whole lot of zeros in it, right? So I'm going to say RC to B. That looks like it's 0, 0, minus 2, right? Yeah? Okay. So what I'm after then is the unit vector of AC dot product with the moment, which is going to be RCB crossed with the force vector. Okay, so let's do the part in parentheses right now. RCB we know is 0, 0, 2. Okay, so let's find the cross product of 0, 0, negative 2 with F. And I'm going to do that on my calculator. Okay. So I'm going to go back to my catalog. Oops, second catalog. I think I'm going to do this. Second catalog. Maybe I just need to hit catalog. Thank you, Andy. Wow, maybe I'm tired too. Okay, the position vector, which I'm going to say, open my square bracket, 0, 0, close my square bracket. Oops, 0, 0, negative 2, close my square bracket, comma, open a square bracket. The force vector we're given in the problem as being 4, 12, negative 3. Close that square bracket, close the parentheses, and I get my moment. So the moment, and we'll say this is the moment about C, is 24 I hat minus 8 J hat plus 0 K hat.
So why do you find the unit vector from AC?
I haven't done that yet. I need to, because I'm trying to find the moment about this axis, right? And so I need to figure out how much of this moment vector lies along this axis. Okay? So let's see, UAC, it looks like I'm a 3, 4, 5 triangle, right? So I think then it would be the unit vector AC is going to be 4/5 I hat plus 3/5 J hat plus 0 K hat. So UAC dot moment about C would be 4/5 times 24 plus 3/5 times negative 8 plus 0 times 0. So 4/5 times 24, that's 0.8 times 24. That's 19.2 plus 0.6 times 8, negative 4.8. get 14.4 pound feet. I did that pretty quick. Please check it. Yeah.
How did you do that one?
4/5 plus 3/5. Because it's a 3, 4, 5 triangle, right? The 4 in the I, 3 in the J.
Okay.
And so then 4 squared plus 3 squared square rooted is 5. Yep. Yeah, Carson?
So the moment force acting along that axis, wouldn't that just be a shearing force though, not a rotational force?
No, because think about, it's a good question. So Carson says, wouldn't the moment acting along that axis be a shearing force, not a rotational force? Okay, let's think about our two-dimensional problem. So before we were living entirely in the xy plane, right? And we said, okay, if I have a force, if this is my origin that I'm interested in, and I have a force acting purely in the x out here of 10 pounds, and it acts a distance, let's call it 4 feet away, then I would say that this has a moment of what? 40, right? 40 foot-pounds. And if I did the cross product of r cross f, I'd get that that is in the z direction with 40 foot-pounds, right? So what this is saying, what the moment vector is saying is, that's the direction, and I'm sorry, it wouldn't be that way, would it? It would be this way. If I follow the right-hand rule, stick my fingers in the direction of r, then curl towards f, I'm going to end up with a negative z vector of 40 foot-pounds, right? What that's saying is, that's telling me the curl direction. So it's really like, that's the axis about which it's twisting, right? So this vector, the moment vector here, says I'm completely spinning about this axis. All right? So then when I do that up here, I find the component I projected onto here. That's telling me the amount that it's twisting about that axis. Twist it. It's how much it's spinning along that. Okay? All right. We have one more section to do in chapter 4. It's section 4.9. Okay? Please read up on that. Yes, Travis?
On, it's supposed to be negative 19.2. Because it's negative 24 times 4.
No, it's positive. That's a multiplication sign. Positive. All right? Yeah, Natasha?
The midterm will cover chapter 4, all of it, right?
All of it, yep. So we'll finish it on Friday.
Yep.
Midterm covers through chapter 4.